Hi everyone, welcome to the Spectroscopy Lab video. So in this particular experiment we have 4 different goals. Our first one is learning to operate a spectrophotometer. And these are also called spectrometers. So you can call it either name, just pick the one you prefer, spectrophotometer or spectrometer. These are instruments that are going to allow us to study how much light a solution is absorbing and at what wavelengths it's absorbing it. And so speaking of wavelengths, what we see is not surprisingly different chemicals are going to absorb different wavelengths of light. And so what we see is whatever wavelength of light a chemical most strongly absorbs, we refer to that as the lambda max. So again, whatever wavelength of light our chemical most strongly absorbs, that's our lambda max. And so moving on from there, we also have Beer's law. So we want to understand Beer's law. And so Beer's law is essentially an equation that's going to relate concentration of a solution to the amount of light absorbed. So this is a method that we can use to find the concentration of a solution without having to resort to things like titration. And also we're going to be learning to find epsilon. So epsilon is a constant that we need to calculate. It's different from chemical to chemical, and epsilon is going to allow us to sort of figure out the relationship between concentration and light absorbed. And then finally, we are going to be practicing Excel. So in this lab, we're going to practice making graphs in Excel. And we're also going to be finding a regression line with Excel. So those are our 4 goals. Learn to use a new piece of chemistry instrumentation, learn a bit about how light interacts with matter, both in terms of wavelengths absorbed and intensity of the light absorbed. And then finally, we're going to do a little bit of playing with Excel. Alright, so you guys are going to have to strap in now because I'm about to cover several decades of chemistry and multiple Nobel Prizes in, 90 seconds or something. We'll see how long it takes. So let's give some quick background about light. So light travels at constant speed. People use the letter c to represent this speed. It's right around 3 times 10 to the 8th meters per second, but there we have it listed to 4 sig figs. Pretty fast. Alright, and so light is generally described in terms of both wavelength, which we use lambda to abbreviate for, and frequency. And this v right here is actually a Greek letter, but heck, we can just call it v for simplicity's sake here. And so they're related by this equation. So essentially our speed of light is going to equal wavelength times frequency, and this allows us to convert between wavelength and frequency. And so speaking of Nobel Prizes, if I remember correctly, this was another Nobel Prize right here, the relationship between frequency or wavelength and energy. So what we saw is that light actually comes in little units that we call photons, and those little units of light, their energy actually varies depending on their frequency or their wavelength, according to the equations right here. And h is known as Planck's constant, and that allows us to figure out, again, that relationship between wavelength or frequency and the energy of those photons. So how does this fit into chemistry class? This sounds like physics. Well, we're about to slam some chemistry and physics together. And so what we see is that all chemicals are going to absorb certain wavelengths of light, and they are going to also be transparent to other wavelengths of light. So this is almost like a fingerprint for a chemical. So a given chemical is going to absorb some wavelengths of light and be transparent to others. So even something we think about as being transparent like glass, while visible light passes through it, things like infrared and UV are actually absorbed by the glass. And then there's other materials which are opaque to, or they block visible light. Those might be transparent to infrared, or they might be transparent to UV. So it just depends on the chemical. They're going to absorb or be transparent to different regions of the electromagnetic spectrum. And so what we see is the wavelengths that are absorbed are going to match the energies of certain particle motions. So what do we mean by particle motions? So, if we think about a molecule or an atom or whatever we have a bunch of particles connected together in a molecule, and we have a nucleus, and we have some electrons around that. And depending on the energy of the light that's interacting with the material, we can get that nucleus to tumble around. That's going to absorb some light when it does that. Radio waves tend to get that type of thing to happen. And we can cause bonds to vibrate like springs, like slinkies, stretching and contracting. That's going to be infrared light. is going to do that. And then we get to higher energy light like visible and UV, because again, the wavelength is related to the energy. What we see is the higher energy light is actually going to make electrons jump around and move, so they can actually break bonds and things like that, or get electrons to move from lower energy orbitals to higher energy orbitals and things like that. So depending on how the particles are arranged in our material, that's going to shift or change what sort of wavelengths of light are going to be absorbed by that chemical. So again, the reason why it's like a fingerprint is because the structure of the chemical actually dictates what types of light are absorbed. Whew, all right, moving on from there. So we can use those wavelengths of light that are absorbed to identify the chemical oftentimes. So this doesn't always work. Sometimes it's kind of messy, but if we're lucky, actually just by kind of shining a light at something under the right conditions and having the right knowledge, we can determine what that chemical is. And so this is incredibly useful not only in chemistry, but biology and physics and engineering, and actually it's really huge in forensics too, because you can try and figure out if something is like gunpowder residue or something based upon the light that it absorbs. So incredibly useful technique. Not as simple as I make it sound right here, very complicated, very challenging, but if you're clever and you have the right gear and the right information, you can often just identify a chemical with light, which is amazing. And so moving on from there, by looking at how much light is absorbed, we can often determine the concentration of a chemical. So if we know the relationship between the amount of light absorbed and the concentration, it's actually a really simple calculation to do this. And we're going to be taking a little bit of a look at both these things here, a little bit of a look at what types of wavelengths are absorbed, as well as how much of a particular wavelength of light is absorbed. So both these two things are going to be addressed in the experiment this week. All right, so let's talk more about this lambda max thing. So again, the lambda max is the wavelength of light that's most strongly absorbed by the chemical. And this again is going to depend on the structure of the chemical, so it's unique to a given chemical. And so we can actually predict what the lambda max for colored chemicals is going to be using the color wheel. And what we see is that they're going to absorb the color opposite on the color wheel. So if we look at something orange, if I try and explain this more clearly here, if we look at something orange, and I gave the example here of beta carotene, so beta carotene gives carrots their orange color, and so beta carotene is clearly orange in color. But what we see is beta carotene doesn't absorb orange light, it's actually going to absorb blue light. So whatever color is opposite on the color wheel, that's the type of light that's going to be absorbed by a chemical. So again, an orange chemical is orange in color, is actually going to absorb blue light. And it's complicated, but that's how our eyes work. And I don't have time to get into it, but essentially we have sensors in our eye that compare the amount of blue and orange light. So if the chemical absorbs blue light, it looks orange to us. That's all we really need to know about it for now. So what that tells us is the lambda max for this beta carotene is probably going to be in the blue range, so in this 430 to 480 range. And right here we have an actual absorbance spectrum for beta carotene. So this vertical axis here is showing us how much light is being absorbed, and the higher our peak, the more light is being absorbed. So that's where we're absorbing the most light. And our horizontal axis here is our wavelength of light in nanometers, and we're often working in nanometers because that's in our visible range right there. And what we see is if we draw a line down, and if we had a computer axis, we could actually measure this much more accurately. What we see is probably right around 440 is where our lambda max is for this particular chemical. And that makes sense because 440 is right in this blue range right here. So our prediction using the color wheel worked. So we could actually guesstimate somewhat reasonably where we expect the lambda max for a given colored chemical to be. And you're going to be asked to do that. You're going to be asked to estimate lambda maxes for red and blue chemicals in this lab. So be prepared for that. So let's talk about Beer's law now. So Beer's law talks about the relationship between light absorbed and concentration. And so Beer's law is listed right here. A is going to represent absorbance. This Greek letter right here, that's epsilon, that represents the molar absorptivity constant. This varies from chemical to chemical, so we're going to have to calculate that in this lab. L is the length of solution that the light is going to travel through, and this is almost always going to be 1 centimeter. So the glass barrier we use in these types of experiments is meant to have a 1 centimeter sort of path for the light to go through. And this is actually going to simplify our calculations a bit because the 1 just kind of drops out. And then finally, our C right here, that represents the concentration. And people typically measure the concentration for these types of studies in moles per liter, though you may see other units as well. And so what we see here is because L is a fixed number and epsilon is a constant, that there's actually a linear relationship between the amount of light absorbed and the concentration. And so it's best to study chemicals with light that's at or near the lambda max. The reason for this is if we look elsewhere in the sort of spectrum, we call it, we don't see as much light being absorbed. So essentially we don't end up with as much signal. And what we generally see, for the most part anyway, to a degree, is the more signal, the better data we're going to get. If our signal's too weak, we're going to get poor data. And we do have some limitations here, and some limitations that have to do with concentration cause this equation to break down. And so if our concentration is too high, what we see is the particles actually clump together in solution. So rather than being evenly spread throughout the solution, they'll stick to each other, and that's actually going to affect our concentration, affect the amount of light that is going to be absorbed, and totally screw up our calculations. So again, if our concentration is too high, the particles clumping or aggregating together will actually throw off our calculations and cause there to be error. We're not going to encounter that in this experiment, but that is something to be aware of. And another thing that can go wrong is if our concentration is too high, then we will not get enough light to pass through the instrument. So the more our concentration, what we see is the more light is absorbed. And if we absorb too much light, we just don't get enough signal to the detector in our instrument. So we're going to get bad data again because we won't have enough signal. So again, 2 reasons why too high a concentration can cause problems. Too low a concentration can cause this signal not to be accurate because the instrument just isn't getting enough signal. So again, if we have too little concentration, our detector isn't going to be able to sort of pick up the light that's being absorbed or detect that there's a decrease in the light passing through the solution because there's so little light change as it passes through the solution. So just things to be aware of. We won't encounter these limitations in this experiment, but in future experiments you might have to deal with these issues of concentration being too high or too low. So I'm going to end part 1 of the video right here, and we'll continue part 2 of the video in the next section.